Hello, scholars. Today we are discussing a multiple regression. So a multiple regression is a test that can predict when two or more predictor variables can explain an outcome variable. So the predictor variables are also called independent variables. They can be called a regressor variable or an explanatory variable. The dependent variable, also known as outcome variable or criterion variable. Okay, so unlike the simple linear regression, which just involves one predictor, a multiple regression can handle two or more predictors and see how they interact with each other on top of it. Okay, so for example, do average hourly temperature and cost predict the number of ice cream cones sold per hour? So I have two predictors here highlighted in yellow: hourly temperature, average hourly temperature, and cost. And the dependent variable is the number of ice cream cones sold per hour. Okay. So like all statistics, there are assumptions about the data and some testing assumptions that need to be true to proceed with this test. So the data assumptions include one dependent or outcome variable measured at a continuous level, which is ratio or interval data, like temperature or number of ice cream cones sold per hour. I'm counting something. And then the other data assumption is two or more independent variables, also called predictor variables, that can be measured either at a continuous or ratio interval or at a nominal level, categorical, like male versus female, age groups by generation, Gen Z, millennial, Gen X, boomers. Okay, so it can also handle categorical variables, and categorical variables requires dummy coding, which was discussed someplace else. Now, the testing assumptions include independence of observations, aka no autocorrelations. Now, this is of the residuals. Remember, the residuals is the difference between our actual data points and the expected data points. So we test that, called residuals. So independence of the observations of the residuals, or no autocorrelations, meaning they're not highly correlated. We test it with the Durbin-Watson. A linear relationship between the dependent variable and each of the independent variables. And we use scatter plots of studentized residuals. And we look at it collectively using a partial regression plot. What we don't do is, if we had nominal variables, that's not part of this test because there's no data points for them. There's just groups. Okay, homoscedasticity of the residuals, or equal error variances. And we use the same scatter plots that we create up here to see if there's a linear relationship. No extreme outliers, which we'll test with Cook's distance. No multicollinearity, which we test with an inspection of correlation coefficients and the tolerance in VIF values. In fact, honestly, we could probably do just tolerance and VIF values since we're using JASP today. And then the residuals are approximately normally distributed, and we create a histogram or a QQ plot. And you already know how to examine those. So for today, our question is, Does job satisfaction and leadership preference predict organizational commitment? Okay. Now, I'm not going to start off with the descriptives. I expect you to know what kind of descriptives you should pull up and discuss with your papers. All right. So we're going to open up our JASP file, and I have labeled our variables JobSat, leadership, abbreviated, and OrgCom, which is organizational commitment. So we do this. We'll go to analysis. We'll go to regression. From the drop down, you want linear regression, right? And then you can move organizational commitments, the dependent or outcome variable, and job satisfaction is a covariate, and so is leadership. Now, for a multiple regression, it does not matter what order the independent variables are, but there are times it does. And when it does, we change our entry method or our models, like model specification. Let's see. I know there's a place to add it. All right, now, last week we talked about a simple linear regression and we had two models. Model 0, which is the dependent variable all by itself, and model 1. In this case, model 1 would be JobSat, and we can see it, right? M1, JobSat. Now, I want to consider another model, job satisfaction with leadership. So I have to add that. So that's going to be model 2. So I'm going to move leadership back over here, and I'm going to put leadership here. Okay. Now this displays correctly. Model 1 is just the dependent variable. Model 2, you can see from the notes, includes just job satisfaction. And model 2, the last one, includes job satisfaction and leadership and their effect on the outcome variable. So this is important. Okay, you'll mostly be looking at model 2, but you'll also look at model 1 by itself. All right, now the statistics I want to order, I'm going to want to order my Durbin-Watson. I'm going to want to order model fit measures, R-square change, and the coefficients and confidence intervals, right? So under statistics here, I'm going to select R-squared change, the Durbin-Watson. Eventually, I want this tolerance and VF test. I want my confidence intervals. Okay, and for Cook's distance, we'll use case-wise diagnostics with, we'll use Cook's distance instead of the standard residuals. Okay, look at all this. So now we have our linear regression with the Durbin-Watson test right here. We have our ANOVA, which tells us how well this model, the multiple regression, fits our question. And then we have our coefficients. Okay, so R-squared tells us how well our predictors in the regression explain the variation in the outcome variable. Okay, R-square adjusted, which we see right here, adjusted R-squared, is the better number to use in the event of bias. It's always just a little bit less than R-squared. Okay. And the R-squared difference tells us how R-squared increases when we add a second predictor. Now remember, R squared tells us how much influence our predictor has over the outcome variable. So if R squared is 0.8, 80% of the variation in that score, like ice cream sales, is due to the average hourly temperature. Or in our example, job satisfaction might explain 80% of organizational commitment. Okay, the other 20% is job factors we didn't consider. Now, we expect that R squared will increase when we add another test. See right here? But ours didn't. Well, R squared did slightly. Adjusted R squared didn't. It went down slightly. Typically, I'm more concerned with adjusted R squared, but R squared for our simple test is adequate, right? So we look at the change. So here's the change. Look. So from the dependent variable, R squared increased by 31.2%, and then R squared increased only another 0.02% when we added leadership preference to explain the outcome of organizational commitment. That's what that means. But let's look at our Durbin-Watson. Now remember, the Durbin-Watson is testing whether the residuals are independent or if there's a pattern. Okay, so here's the null hypothesis, is that there's no autocorrelation in the residuals. They are independent. So failure to reject the null means my assumption is met. If I reject the null, the assumption is violated because there is a statistical significance and there's autocorrelation of the residuals. So I have it written down right here. So you can look at just the DW statistic highlighted in green, or you can look at the p-value. I usually report both if it gives it to me. The p-value makes it very clear. Is there a significance? We hope to get greater than 0.05, our alpha for social sciences. Okay. But if we get less than, the assumption is violated for that model. Remember, I'm not so concerned about model 0 because it's only an independent variable. Of course, there's no autocorrelation. But here's model 1, and that's just job satisfaction. And the DW statistic is 1.905. P equals 0.707. So that assumption's met for model 1. For model 2, the DW statistic is 1.869. Both of these are close enough to 2 that I don't need to worry about it. Remember, we need to value around 2. But I have my p-value if I'm not sure. My p equals 0.599. That means that there's no statistical significance. We fail to reject the null. The assumption of no autocorrelation or independence of the residuals is met. Okay, and you can see right here how I write this out. There was independence of the residuals as assessed by a Durbin-Watson statistic, and I give the DW statistic and the comma p-value for the intercept, which is model 0. I give it for model 1 and for model 2, written out the same way. Okay. Now our next assumption is to test for linearity. And we can see I'm going to add these plots now in JASP. I'm going to scroll down to plots down here, right? And I want to check residuals versus covariates, probably residuals versus predicted. I want that residuals histogram to check for normality. If you like QQ plots, it's right there, right? And I want my partial plots. And you can leave your confidence intervals set at 0.95. That goes with our alpha being 0.05. Okay, and now you'll start to get all these plots down here. Okay, they'll slowly show up. Here's my histogram of the residuals. That looks approximately normally distributed to me. Okay, here's residuals versus predictive value. This is a collective, and we also use it for homoscedasticity. And then here's our partial regression plots here. So let me break down how to look at each of those. Okay, so we'll have all of these different outputs, and I'll have two sets of some of these scatter plots because I have two independent variables, job satisfaction and leadership preference. Okay, so to check the residuals for linearity and homoscedasticity between the residuals and job sat, I've marked it for you. Those are the ones marked residual versus covariate. And we want one for job satisfaction and one for leadership. To check the residuals collectively, this is the big one for homoscedasticity. This is the one we always use. It's residuals versus predicted. I circled it in green, but you can see it. Residuals versus predicted. This is our histogram for normality. And then our partial regression plots, where we're checking organizational commitment versus job satisfaction and organizational commitment versus leadership. Okay, now look at this. The partial regression plot shows organizational commitment versus job satisfaction shows the relationship after controlling for the effects of leadership. You see that? So this plot right here, the first one, the effects of leadership is already controlled for. And the same thing for the partial regression plot shows the relationship between leadership and organizational commitment after we control for job satisfaction. Okay, so we want to look at each of these plots, and basically we want to make it look like that there's some sort of linear relationship starting to form. So here's some examples of what would be considered linear, okay, of the residuals. And here's examples of nonlinear. So we don't want U-shapes and curves and things like that. Now, typically this one would be considered a non-linear relationship for a correlation, but that's not what we're testing here. So this complete horizontal line is acceptable. Okay, now if we scroll up and we look at mine, I'd say these assumptions are approximately met. I would say the same for these. We can look at the line going in between. I'd call that approximately met. Okay. So, and for homoscedasticity of the residuals, right here, we don't really want a pattern. Okay, so no funnel or fan shape. So you got to go back and look at that scatter plot a second time, right? There's no funnel shape. There's no fan shape there. This would be violated homoscedasticity. Okay. And then I told you we can look at the normality of the residuals. I'd call this approximately normal. It's not perfect. So I would say the assumption of linearity is met. I would say the assumption of homoscedasticity is met. Okay, now what do I do if these things aren't met? I discuss that in each of these places. Okay, for example, if there wasn't independence of observations, I would change my test to a generalized least squares test, right? If linearity is violated, okay, I might consider a data transformation like a box Cox method, or I might change tests to the Ramsey reset test, aka regression equation specification error test. You know I don't like data transformations. I typically will change tests. Okay. And if the assumption of homoscedasticity is violated, I would change tests. You could transform the data, but I would use a weighted least squares regression. Now, for the sake of your homework, just proceed. Make your recommendations. Now, the next assumption we test is the Cook's distance. Cook's distance will identify an outlier that is having an extreme influence or too much influence on the model. It could be causing violated normality, violated linearity, or whatever. So that's why we identify them. Okay? So it's like asking, if we removed this one observation, how much would the regression line change? Okay? Not all outliers are influential, and Cook's distance helps us spot any ones that are actually hurting our regression model. All right. So I already showed you how to order it. We'll just go back and look at the output. But if I'm using Cook's distance, I want the Cook's distance statistic to be greater than 1. I'm sorry. If Cook's distance is greater than 1, it's too big. It's too influential. Forgive me. And you can see that right here where I showed you can order this in JASP. Cook's distance greater than 1, because I could put that number there and it'll report it to me. Now, here was my results. There were no influential cases found in any of my variables. Okay, but you might have one. So we would get the case number, which case was causing a problem, the residual, the organizational commitment score, the predicted value, the residual, and we would get Cook's distance. So right here is where we would be looking to see if it was greater than 1. So if Cook's distance is greater than 1, it's possibly influential. And in small data sets, even the unusually high values, like say it's, 0.45 and all of them are like 0.1, they might be causing problems too. So with an outlier, we usually investigate. First, we check and make sure if that data point is correct. If the data point is correct and it belongs there, because sometimes there's a mistake in our sampling and we might catch. If the data point's correct and there's not a mistake in our sampling and we cannot justify removing it, we might transform it through a complicated method. We might just remove it, but we would test and see if removing it even changed your assumptions. So usually you'd remove it and test the assumptions again and see if it changed anything. Now, our next assumption is no multicollinarity. And we test that we can do an inspection of correlation coefficients. Anything greater than 0.7 is a problem, so that's like a Pearson R. Or we can inspect it with the tolerance and VIF values. And that's what we're going to use today. So I already showed you how to order that. Under statistics, you're going to select under coefficients, you'll select estimates, confidence intervals at 95%, and tolerance and VIF. Okay, now here's what our output is going to look like. And I've highlighted in yellow where tolerance and VIF is. Okay. So we don't want collinarity. That's when there's too much overlap in independent variables predicting with the outcome variable. So they're kind of like just overlapping a lot. It's hard to separate what's what. So it measures how much of a predictor's variance is not shared with other predictors, because some of that's shared. So we want, if the tolerance is greater than 0.2, it's safe. If the tolerance is less than 0.1, that's a red flag. Okay. So tolerance, and I'm going to look at my models. There's model 1. Well, there's 1 because it's only considering one variable. So, but I'm concerned with model 2 on this because it has both independent variables. Mine's 0.2 on both. So that's good. We're good there. And I can look at the VIF, which basically is times 10 of the tolerance. Okay. So the VIF, variance inflation factor, it should be, if it's less than 5, it's acceptable. If it's greater than 5, it's a concern. And if it's greater than 10, you've got a problem. Mine's hovering at about 5, so we're good. Okay. Now, if you have low tolerance, this means that a predictor is leaning too much on the other. So if I had low tolerance, it would mean that either job satisfaction or organizational commitment is depending too much on the other variable. Okay. So this means that my answers would start to get distorted. So my assumptions met. So I'm going to report it like this. Culinary statistics indicated no multiculinary concerns. All predictors had tolerant values above 0.2 and variant inflation factors below 0.5. Okay, now, if your assumption fails, it means one of the variables is highly correlated with the other. Typically, we take the offending variable and drop it from the test. Okay, and then we proceed. So you might end up, if you had to drop job satisfaction or leadership preference from our test, you'd be proceeding with the simple linear regression. Okay, but we just drop the offending variable. Okay, and now it's time to interpret our multiple regression. Okay, so first we're going to interpret R squared by the model. So we're going to look at model summary with organizational commitment, the outcome variable. Okay. So looking at model 2, the first thing we want to do is look at R. Now, R is simply the Pearson correlation coefficient between the scores that are predicted by the regression model. Okay. If you look at mine, model 1 is a 0.312. Oh, I'm sorry, R is a 0.558. That's a moderate effect. Think back to learning your Pearson R and your correlation tests with Cohen's cutoffs. 0.5, 0.6 is moderate strength. And model 2 is a 0.56. That's also moderate. Okay. Now, the next thing I'm going to look at is my R squared and my adjusted R squared. Okay, a lot of people will just use R squared. Adjusted R squared controls for bias to make sure the test isn't overinflated. So my R squared for my model 2 is 0.314. If I turn that into a percentage, this means that job satisfaction and leadership explain 31.4% of organizational commitment. But look at this. Job satisfaction all by itself explained 31.2%. So it looks to me like most of what explains organizational commitment in my case is job satisfaction. Now look at the adjusted R squared. It's adjusted for bias to make sure that our test isn't too strong. Adjusted R squared says 30.1% of job satisfaction explains organizational commitment. But when you add leadership to it, my adjusted R squared went down 29.2%. So leadership preference actually took away from organizational commitment if I interpret adjusted R squared. Usually we would look for that to go up. This went down. Okay. So adjusted R squared corrects for adding things if there's nothing meaningful added. Now look at that. There was nothing meaningful added by including leadership, and we see it in adjusted R squared. That's why we look at it. Okay, this helps with bias. Nothing meaningful was added. So if we looked at R squared all by itself, it looks like, well, it added like, 0.1%. But when we adjust for these problems, it actually took away from the model. So leadership preference doesn't really explain organizational commitment. Now, RMSE stands for root mean square error. This tells you how far your predicted values are from the actual values in your data set. Okay, so if you look at mine, RMSE, on model 2, mine is 1.363. This means that each prediction for mine is off by about 1.363 units for each score, or on average. Okay. Now, the next thing I want to do is report statistical significance, which I've highlighted here. Here's my degrees of freedom. So, look at this. Model 1 was statistically significant. P was less than 0.001. So leadership, statistically significant, significantly predicted organizational commitment. Look at model 2. Leadership and job satisfaction, that did not. So when I added leadership to job satisfaction, this was not a significant improvement. So I would not say that leadership helps explain organizational commitment at all. All right. So the next thing we're going to look at now is our ANOVA table. And the ANOVA table answers the question, does the full regression model explain a statistically significant portion of the variance of the outcome variable? Okay, so does it explain, does job satisfaction in model 1 explain a significant amount of organizational commitment? And in model 2, does job satisfaction and leadership explain a significant amount of organizational commitment? Okay, now look, here's my F for an ANOVA. You guys remember what that is, right? And here's my p-values. So basically, the ANOVA table is answering the question, is this model a good fit for my test? Okay, yes, it is. This model is a good fit for my data. That's all that means. Here's how I interpret it. So I highlighted everything, how I write it out. We write it out the same way I showed you how to write an ANOVA. F with the degrees of freedom, remember that's a fraction. equals 21.095. I rounded up to 10, comma, P equals 0.001 for model 1. Job satisfaction alone significantly predicted the outcome. Model 2, just to see if it was a good fit for the data. The model is a good fit overall, okay? Because notice in our test up here, we didn't have that significance, right? Let me explain. Okay. If you look at the F value went down. If adding leadership helped explain more of organizational commitment, the F value would have gone up. It went down. So while it has something to do with explaining the outcome, it wasn't a strong predictor of organizational commitment. So leadership preference by itself and with job satisfaction doesn't really do a great job of explaining organizational commitment. But this model, a multiple regression, was a good fit for the data. That's the best way to think of the ANOVA test. This tells us whether or not a multiple regression is a good fit for testing our data. Okay. Now, the last thing we want to interpret is the coefficients. So that table came out here. Okay, so let's look at it on my handy dandy paper here. And I've color-coded everything. Now, I want you to notice first, when we look at the negative numbers in front of the unstandardized, the blue, you see that leadership has a negative number. This means there's a negative relationship. So unstandardized coefficient B, this tells us how much the outcome variable changes for each unit, 1 unit increase. So each time we increase one score by 1 unit in the predictor, it tells us how much the outcome variable changes. So with job satisfaction, it changes 1.408 units. With leadership, it goes down 0.151 units. Okay. So in my example, B equals 0.105. For every 1 point increase in job satisfaction, organizational commitment increases by 1.05 units. Now, standard error is the uncertainty around the estimate. The smaller the standard error, the more precise. So we prefer a small one. All right, right here, it's in green. That's pretty small, 0.38, 0.344, that's pretty good. The t-value and the p-value. All right, so these test whether each predictor contributes to the model by itself. So just look at model 2. Job satisfaction significantly contributed to the model, p equals 0.008. So I would literally report that. We'll get to that. Lost it. We would report that. Okay. Now let's look at leadership. Leadership, again, was not a significant predictor. So it did not significantly contribute to the explanation of organizational commitment. Okay. And then the standardized beta, circled here in pink. All right. This is useful if I want to compare which predictor has a stronger effect. because they're both then used, the same scales used. You know, like if we measured leadership on a 5-point scale and we measured a job satisfaction on a 7-point scale, those scales aren't the same. The standardized beta puts everything on the same scale, so we're comparing apples to apples, right? Job satisfaction is 0.651 and leadership is minus 0.014. Again, a negative relationship. So job satisfaction has the bigger number and the stronger effect. In this case, the negative sign doesn't really matter. We're looking for the larger number. Okay, so here's how I would report this in APA. A multiple linear regression was conducted to examine whether job satisfaction and leadership preference predicted organizational commitment. The overall model, this the ANOVA, was significant. F, my degrees of freedom, my F statistic, comma, P was less than 0.001, and it explained approximately 31.4% of the variance, which is R squared, 0.314, in organizational commitment. Job satisfaction was a statistically significant predictor. Remember the t-test? There it is. That's where I report it, right there. So I'm going to give my unstandardized B, the standard error, and the beta. I report all of those. My t-test right here, and then my confidence intervals. And I will do the same thing for leadership. But remember, leadership was not a significant predictor. P was greater than 0.05. But I'm going to report it the same way. Now that I have my results and I've explained them, it's time to draw my conclusions. So here are some considerations. Was the model, the ANOVA, significant overall? Yes. How much variance does the model explain? I can look at R squared or adjusted R squared and say how much, especially with model 2, how much is explained. Then I look at each predictor. So I'll look at leadership, model 1. I'm sorry, I'll look at job satisfaction, model 1, and then I'll look at leadership. And I went above. We talked about that above. All right, what direction is the effect? Is there a negative relationship on the sign of B? Okay. Is the effect big or small? We had moderate effects. Okay. Leadership was a negative relationship. Job satisfaction was a positive one. And only job satisfaction was a significant predictor. Leadership did not. That's a conclusion. So, what can I claim about all of this? I can claim that adding leadership preference does not help explain organizational commitment. It did not contribute much to the model. Most everything was complained by job satisfaction, and it was a positive relationship, explaining about 31% of the variability in organizational commitment. Now, both models were statistically significant in the ANOVA, right? But remember, my F value went down for model 2. So that means leadership didn't improve the model. So the multiple linear regression was a good fit for the data, but adding leadership did not improve the outcome. So R squared improved only slightly in model 2, and it did not improve, it decreased when we used adjusted R squared. So leadership didn't help. Okay, so draw your conclusions. Do you reject the null? Or do you fail to reject the null? The null hypothesis, let's go clear back up here. Remember to state whether or not you're rejecting your null. The null hypothesis states that job satisfaction and leadership preference do not predict organizational commitment. Well, we can reject the null But we have to qualify that. Only job satisfaction helps predict organizational commitment at 31.4%. Okay? So you can look at some of these things for writing up. Okay? And some considerations when you evaluate your own data. As always, if you have any questions, reach out to me. Thank you very much.